device technology. This is the last topic in EDC. It is actually included in electronic devices and circuit for one purpose, to really make you to learn how to fabricate an integrated circuit. Because we have seen the fabrication of diode, BJT, FET, and finally we are going to see how ICs are being fabricated. That's called device technology. The topics included in this are integrated circuit fabrication process, and the second topic is CMOS process, that is called NMOS, PMOS, and if N-tub and P-tub are combined together, it is called twin tub. Tub means like a tub. Now we'll go to the first topic for first lecture, integrated circuit fabrication process. Before I really teach you the actual process of fabrication, I'll be teaching some fundamental definitions in order to understand the lecture. Let's go to some fundamental ideas. General classification of integrated circuits. What is the classification? There are several ways that ICs can be classified. It can be based on the fabrication and based on the category of fabrication. The first one, based on the fabrication, monolithic ICs and hybrid ICs. Then based on the application, analog ICs and digital ICs. In fact, nowadays we have got a new idea called mixed ICs. Nowadays we have something called analog digital mixed simulators. We call ADMS, mixed simulators. It's more like a IC fabrication in that we have VLSI. So it is not VLSI in our GATE exam, but it is an introduction to VLSI that makes us to understand IC fabrication. Because in analog circuits we are going to study ICs. And before we really study the applications of ICs, we need to understand how they are fabricated in devices. The different levels of integration of ICs. SSI means small scale integration, 0 to 10 logic gates in that particular chip. MSI means medium scale integration, 10 to 100. LSI means large scale integration, 100 to 10,000. VLSI means more than 10,000 up to 1 lakh. There is one more, of course, that is called ULSI, ultra large scale integration, that is more than a lakh. As of now, we are already in the technology of ULSI. Features of hybrid technology. Hybrid technology has two types of technologies. One is thick film and second is thin film. Thick film, what exactly it says? Using thick film technology, high density circuits containing resistors, conductors, capacitors, all such things are fabricated at low cost. Active devices like diode, transistor, integrated circuits are also developed at a low cost. So, and hence it is called thick film technology. And because we are taking passive components and active components, we call it as hybrid technology. Second, thin film technology. Thin film technology is used in the field of microelectronics, in which conductive resistors, dielectric films are deposited and insulating material is also developed. That is called thin film technology. For example, after making ICs, you develop some silicon dioxide layer, that's called thin film technologies. So these are the two types of technologies, thick film and thin film. Let's see monolithic ICs. The basic meaning of monolithic is developing so many components upon or on the top of one single silicon substrate. Actually, monolithic is a Greek word. Mono means single, lithic means stone. On a single stone, we develop lots of components and ICs. And it is very popular. Even in our Indian culture, we have so many things. Even 1,000 pillars developed on a single stone. So many big temples are built on a single stone. So single stone technology was a very old technology. But that was in the olden days was meant for really on the developing all these things on a single stone and a rock. But the same technology is developed now on a single silicon wafer. Actually, what is the stone here? Here the stone is silicon material. So on a single silicon material, we develop all these components required, and that's how the ICs are coming into the world. And that's the main purpose and the main point about monolithic ICs. Then coming to the technology, the processing steps used to fabricate various devices such as diodes and transistors, integrated circuits as follows. Diffusion, which can also be called an alternative method of ion implantation. Oxidation, photolithography, chemical vapor deposition. Fifth one is metallization. These are the basic steps by which we fabricate devices such as diodes, transistors, and integrated circuits. Now let's understand one by one. What is diffusion? It is used to form base, emitter, and resistors in a bipolar transistor. They are basically for active elements. We use such a technology just like mass devices. The word diffuse means send it. Ion implantation. This is an alternative method of diffusion. We don't really send them in. We give some potential outside. Using that potential outside, this being developed within the material. That's why it's called ion implantation. That is, in this process, dopant atoms are vaporized, accelerated, and directed at silicon substrate. They enter the crystal's lattice, collide with silicon atoms, and gradually lose energy, finally coming to the rest at some depth within the lattice. The average depth can be controlled by adjusting the acceleration energy. So when you say ion implantation, it's not like a diffusion. What we do from outside in the process of diffusion, we also do from within, that is called ion implantation. Therefore, diffusion and ion implantation are two different methods of same thing. Oxidation. Oxidation is basically when you have material, we need to put oxidation material there. With that, you can have so much of immunity and no interference and noise can affect the IC which is inside. So the electrical properties of oxidation uses are, it is used to mask against implant or diffusion dopant into silicon. As I said, implantation or diffusion has been done. Once this is done, we need to provide isolation so that this will not have any effect from the external. And it acts as components in mass structures to provide electrical isolation when there is a multi-level metallization system. So basically, after doing the oxidation and ion implantation, after doing the diffusion and ion implantation, you can go for oxidation. How does it come actually? Silicon plus O2, silicon dioxide layer. Silicon plus 2H2 is SiO2 plus H2. That's how the vaporization is done, and finally SiO2 layer is deposited on the chip. This SiO2 layer is really making isolation from the device with the external fields. Indirectly, the input impedance the impedance for the IC is almost infinite or infinitely large. Photolithography, as photo means light Litho means again stone. Graphy means cutting. That means cutting the stone, that means silicon dioxide layer, using the light, that's called photolithography. So what are these different ways we do it? There are three structures using this. It is derived from printing plates, and usually the wafer is of silicon dioxide layer that coated with photosensitive material, photoresistant material, and we normally expose it to ultraviolet rays through mask of structures. In fact, people use ultraviolet rays or X-rays. Some high frequency radiation we have to use so that that particular portion of the material can be removed so that you can put something inside. So photolithography is removing wherever unnecessary portion is required. Etching, removing film unprotected by resist. Striping the resist, leave only pattern film. So this is all about photolithography, what we do in this IC fabrication. Next one, chemical wafer deposition. We call it as CVD, chemical wafer deposition. CVD is a deposition of a solid material onto a heated substance via decomposition of or chemical reaction of compounds contained in the gas passing over the substrate. Any material such as silicon nitride, silicon dioxide, polycrystalline single silicon, and a single crystal silicon can be deposited via CVD. So this is about chemical wafer deposition. A special case of CVD is called epitaxy. Epitaxy means one upon the other. Epitaxy layer deposited a wafer of vapor phase epitaxy, in which case the deposited layer is in a single crystal form. So this is also a process where chemical vaporization is also taken care in order to do the ICs. Next one, metallization. What exactly metallization? For example, you have made IC completely, but suppose there are so many components, you want to enter into the component or you want to connect one component to the other component. We need a metallic contacts. These metallic contacts are definitely required, and they are also connected in order to have a connection from the metal, the component, to the external world. Wherever you are using this application, you need to connect it. Therefore, all the chip which is inside should have metallic contact. But what are the properties of a metallic contact? Some people think metal means that is having a metallic contact. Sometimes we also call ohmic contacts. What exactly they do? The moment I say ohmic contact, people think that has a lot of resistance. That's not true. Ohmic contact means that is having low resistivity, easy to form, easy to etch, should be stable. Why all these properties? Suppose if the metallic contact itself has a lot of resistance, all the current that you are sending in, that doesn't go into the component, but they're stuck up there. This just got stuck up. Let's go to illustrative examples. Illustrative example. Problem 1. Explain the simulation and synthesis steps in fabrication of ICs. Solution. When you're fabricating IC, look at these steps. There are generally 6 levels. First one, design idea. Second one is behavioral level. Third one, data flow level. Fourth is structural level. Fifth is physical level. Sixth one is fabrication level. And first 3 levels are generally called simulation or analysis. And the last 3 levels are called synthesis or design. Generally, before any synthesis or design, the simulation go ahead. Simulation will go. Simulation is there. Now let me explain you step by step First one is design idea. It is an idea that you wanted to do something. Suppose you are walking on the road, you see some accident is happened, and you want to make some chip for avoiding the accident. That becomes our idea now. Or you are going on road and you saw some fire accident. Before the fire accident come, you want to have some smoke detectors or anything, and that's an IC that you have to make. So like that, different practical day-to-day applications are the ideas for design. That's why design ideas are three types. First one, verification of existing design. Suppose already the design is there, we need to verify whether it is working according to expectation. Actually, the verification of existing design is not doing or inventing a new chip, but it is to learn what has happened already. Indirectly speaking, you are not designing anything, you are just understanding it. It's an understanding process. That's why, for example, 8051 is a chip that you have. In the 8051 chip, how do we really achieve this? How they achieved, and you need to check it, you write a program and implement it, that becomes your project or your problem now. That's idea. So when you are verifying an existing design, we generally call a BTech project. And when you come to design idea, the second design idea is modification of existing design. After you really verify the design, you'll really go for, if there is a modification possible, that's called modification issue. And that's why I normally call it as MTech project. And you see the last thing that I have mentioned here, in the design idea, it is invention of the existing design. We want to invent some new things, That becomes PhD. So let's go for behavioral level or mathematical level. For example, you have seen the IC here, inputs are here, outputs are here. Why it's called behavior? This will tell only the behavior between inputs and outputs. It simply says the behavior between inputs and outputs. It will tell the truth table that gives input and output. Sometimes it will give you mathematical equations between input and output, and sometimes it will give you algorithm between inputs and outputs, and therefore it has the highest abstraction. When I say it has the highest abstraction, it means that anybody can understand. When you go down, that becomes highly technical. That's why people may not understand. But this one, everybody understand. It's only a truth table or mathematical equation or algorithm. That's about basically behavior. The word behavior means the behavior of the design. That means the relation between inputs and outputs. That's the thing that we need to take when you are really going for ICs being fabricated. Then the third level, we call it as data flow level or block diagram. For example, there is a full adder circuit. We take half adder and half adder. When you take two half adders, we are indirectly saying each one is a sub-block, and therefore it's called a block diagram level. What is the meaning here? Is the hardware is clearly known to you? No. Is the hardware not at all? No. We know it. We know partially. That is in terms of blocks. When you really say blocks and impartially, we call it as a data flow level, because data is flowing from input to the output through the blocks. That's why the word came data flow level. And in MATLAB, we call it as a Simulink. And that is basically saying higher design in terms of a smaller design. That's why we call it as a block diagrams or data flow level. That's the third level in which we want to do it. And all these three levels is called simulation or analysis. Actually, when you say simulation, there are EDA tools. EDA means electronic design automation. Electronic design automation tools are already available. You can use them in order to verify the design. And never go for design without verification. Suppose you go for design, you really fabricate it. After that, you find something going wrong. You can't waste your whole design. That's why simulation comes before synthesis. What exactly simulation tools? There are two types of simulation tools. One example is model sim. Model sim, the word model sim means it's a model for simulation. What does it do? It can simulate irrespective of if synthesis is possible or not. Even if that may not end up in a synthesis, it may not end up in a design, still it says it can be simulated or it can be analyzed. Just like saying this can happen, finally it may not happen. That is what it means. Whereas the second thing called Xilinx, simulation is possible only for the circuits that are synthesizable. Suppose it cannot be synthesizable, you don't even check for simulation, or the tool that cannot check for the simulation. So synthesizable things are simulated is called Xilinx, whereas in model sim and tools like that, it can simulate even if it is not synthesizable. Then let's go to the next level. That's called structural level or symbolic level or logic level. What exactly comes here? When you go for further down, and it will give you hardware in the form of symbols, hardware in the form of structures or logic gates. For example, if I put a NAND gate here, for example, you take a full adder and block diagram came, that's called data flow, and when you go to structural level, you will get the total thing in the form of structures, symbols, for example NAND gates. So we call it as, they are called device level or symbol level in that. Next one comes device technologies, that is actually IC. What happens is, when you go for device level, we call it as a physical level. What is that physical level? The physical level basically means the whole design is in the form of physical devices. That's why EDC comes into picture. And after the actual circuit came, we can go for fabrication. That's called IC fabrication. And that is actually we call device technology. What's the advantage of device technology? Small in size, less power consumption, high speed. These are the device advantages. That's about the first problem. Now let's go to second problem. What is the general sequence of fabricating integrated circuit? What are the steps we take? Solution. Crystal growth. First we have to get a crystal. Then wafer preparation. Out of that crystal we need to prepare the wafer. We call it a substrate. Upon the substrate we have to go to epitaxial in order to put something upon it. After putting the epitaxial, you should go for oxidation. That means silicon dioxide layer has to be developed. Then wherever it is unnecessary things are there, any extra things we want to put it, you have to do lithography, as I told you. And after lithography is done, whatever portions are removed, they are ready. You can go for reactive plasma etching, polysilicon film deposition done. Then we go for diffusion process. After that we go for ion implantation, finally metallization. Once metallization is done, the components are available to you. That's the real steps of IC analysis. Question number 3. Obtain a chip for the given circuit. For example, this circuit is given capacitor, diode, transistor, resistor. There are 4 components. How do you put all these 4 components on a chip? I am really coming to the real essence of this topic called fabrication of a chip for a given circuit. Actually, this circuit is available. If you see from my block diagram and flow diagram, that is after the physical level, just before fabrication. So from the design idea, it goes to behavioral, from the behavioral to data flow, from data flow to structural level, from structural level to device level, and then this circuit is achieved. For this circuit that we achieved, we are going to make a fabrication and make a chip for it. I am really going to tell you how the chips are being made in industry. Everybody knows today chips, even a layman knows what ICs are and what chips are. And this is the process I am going to explain. It has taken 10 steps of process before you really get an IC into your hands. That's why I said IC, everybody says IC and IC, but they don't see anything because everything inside is closed. Okay? And the idea that you have in your brain should come into your hands, that a chip. All that idea that you have in your brain should be implemented as a chip, should come into your hands. And nowadays so many chips are being in the market, Every day new chips are coming into picture. So let's see now the actual process of chip formation. This is what the device technology is expected. The first step. Step 1. Silicon wafer P substrate. So look at this. You have a crystalline puller. In this you put the liquid and rotate this, and all this is silicon dioxide layer is deposited on this. If the silicon dioxide layer is deposited, remove that and cool it outside. When you cool it down, all that liquid form has been deposited there. Once that deposition is there, you remove the scratch from that, and that scratch itself is called silicon wafer. Nowadays people are talking about biscuits, and so many wafers are there. And that's what exactly wafer. A small thin layer, we take it. Upon that substrate we develop our IC, and that substrate or that process is the silicon wafer. We call it as substrate, and that's called P+. So silicon melt is deposited, taken out and cooled it, scratch is removed, and the scratch is called silicon wafer from now. So this is called heavily doped silicon wafer, and this is P+. Now understand, out of this stone I am going to develop IC for the given circuit. Because this is a single stone, we call it as lithography. As I told you, monolithics. In monolithic IC, we are going to develop IC, and the circuit I am going to etch upon that, like somebody is making this table or a chair or something. They're all doing the same. We are also doing the same in ICs. Step 2. Step 2 is called epitaxial. We are going to bring a small thin layer is just put from upon this. That's why it's called N. So this is NP capacitor, PN diode. PN is not a transistor, it requires another material, but we have to make one more. That is what we call it as diffusion or ion implantation. But this is PN, small layer is N. This total is P, small layer is N. Therefore, it is PN resistor. This monolithic material I have divided into 4 components. Because if you see the circuit that they gave, first we have a capacitor, then we have a diode, then we have a BJT, and finally we have a resistor. All these things are put into different forms. This is how dividing. We have divided the material into 4 forms there. Step 3. SiO2 layer. After doing epitaxial, you can go for SiO2 layer. What does SiO2 layer do? As I already mentioned, oxidation is done. Oxidation means you have isolation. It has been protected from external interference. Along with that, input impedance also increase because silicon dioxide layer produces high input impedance. That's what exactly happened in MOSFETs. Step 4. Photolithography. As I told you already, we are going to, any portion is required to be removed, we apply photolithography. In the olden days, people use X-rays, but in the later days, now they are using electron beam. Now using electron beam, people are removing wherever the portion is required so that they can put some other extra material from outside. Step 5. Diffusion. As I told you, a small portion is being removed. Look at here, I am going to diffuse a material. Now what happens is N here, P here, and N. So NPN becomes a transistor. That's the meaning of what you call diffusion process. After doing this diffusion process, whatever that we have etched or removed using photolithography, we close it. Step 6. Ion implantation. The required N layer, instead of sending from outside, is developed from within, and the process is called ion implantation. Therefore, diode is achieved. Because as I told you, diffusion and ion implantation are 2 alternate methods of the same. Note, diffusion and ion implantations are 2 different methods of the same thing. So now we have transistor is available, diode is available. Actually, transistor is converted into diode. How a transistor is converted to diode? If collector and base are connected, it's no more a transistor but a diode. So, seventh step, isolation of components. So far, all the components are available side by side. You have seen capacitor, diode, transistor, resistor. But if they are all together, mixed together, it's a dangerous thing. So, you need to isolate them. In order to isolate, we put some dielectric material between them, or the junction itself will act as a dielectric material. So that is called isolation. Though these four components are side by side, they have been isolated. Now they are not connected to each other. In fact, they are isolated or disconnected. Only when we connect from outside they are connected. Otherwise inside they are not connected. That's called isolation. Step 8, metallization. What is metallization actually? All these components got ready now. Whatever the connections you have to make now, you should put a metallic contact there. For example, capacitor and diode should be connected. You should put a metallic contact. Look at here I am doing. As first one is here. This is not actually connecting a component. It is getting ready for the next IC if you want to attach it. So this is a capacitor. Capacitor to diode we have connected. Diode to transistor it is connected. Transistor to resistor is connected. And finally, sixth element is available for VCC. So like this, the chip is ready for a 6-pin chip. All the 6 pins are here. This is SiO2 layer. Upon the SiO2 layer, we have metallic contact. Step 9. On a single silicon wafer, or on a single silicon substrate, we make millions of ICs. For example, 741, MUA741 is op-amp. So don't think each one is made one by one. On a single silicon wafer, lakhs of ICs or millions of ICs are made, and all those millions of ICs now should be removed so that each one can be used. And the process of removing them is called assembly. Lastly, package. When the IC is ready, you need to pack it. For example, you must have seen so many ICs. Most of the ICs are packed because for example, take the laptop, you can see every IC is inside and been packed. Not only that, each IC is packed with material. How to pack it or why should we pack it? Because if the IC is externally available, it will damage. So pack it into with a material. Generally we use ceramic material, but that is costly. Whereas the plastic material is cheap. That's why even in any IC you see a plastic material. Most of the ICs are plastic material for domestic purpose and industrial purpose. Only for R&D purpose maybe we may go for ceramic material. Otherwise all are plastic material. The good thing about plastic material is cheap, but bad thing about it is when it falls on the ground, it will break. The total IC will be broken and becomes useless. So this is the 10-step procedure of fabrication. That's the basic thrust of the device technology. Now let me go to the fourth one. Why silicon is used in ICs? Question number 4. Silicon has become more popular for so many reasons. First reason is its energy gap is high. When the energy gap is high, we say it can immune to the noise. Second reason is temperature range. It can bear any temperature for a large void of temperature. Whereas germanium, it has a less range of temperature and cut-in voltage is very less, therefore it cannot bear noise. Suppose a noise of very small comes, it will be affected. And lastly, one thing you must understand, the resistivity. For silicon, the resistivity is 23,000 ohm centimeter. Very high resistance. Whereas for germanium, it is 47 ohm centimeter. 23,000 is very high. When the resistivity is very high, it cannot conduct. Not conducting is a good point because it can withstand noise. That's why we say silicon is only one side, it's acting as a switch. Therefore, silicon became the greater important material as far as the ICs are concerned. And therefore, for any technology, whether it is CMOS technology or BIMOS technology or any technology, silicon became. Actually, as a matter of fact, nowadays, the technology became silicon technology. because silicon by default is used for the reasons I told you. Question number 5. Which metal is used in metallization process? Just now we said we have to make a metallization at the end of the fabrication. Which end is used? What material is used? Solution. Its answer is very simple, straightforward: aluminum. Aluminum is basically its most commonly used material for metallization for transistors and diodes. And its conductivity is also good. That's why aluminum is a good one. If you see the advantage of aluminum, it has a relatively good conductivity. It is used to deposit on thin films. It has a good adherence to silicon dioxide vaporization. Aluminum forms a good temperature range also, and it has a low resistivity. And finally, it can be applied and patterned in a single silicon deposition. So this is different advantages of aluminum. Therefore, for metallization, we generally go for aluminum. Question number 6. What are the advantages of ICs over discrete components? Now that's a general question everybody asking. Why people are so much interested in ICs? The solution. IC technology offers reduction in size and weight. The size is reduced. And it increases reliability, because if discrete components are here and there, they're just scattered. Even if air comes, air blows, it will spoil. The reduction in circuit cost also. Reduction in power consumption and improvement in speed. There are several advantages in ICs. That's why nowadays 99% we go for every design as ICs. Question number 7. How isolation is obtained in ICs? How the isolation is obtained? In IC, as I told you in the beginning, if you want to make an isolation, the best thing is put some dielectric material between component to component, and then you go for or junction as a dielectric itself. So there are several ways, but junction is very much preferred. But somehow you have to isolate one component to the other component. Question number 8. Explain p-n junction used as isolation. Actually, p-n junction is having ions in, because after the recombination ions form. Because of ions form, junction is developed. When the junction is developed, we call it as isolation technique. That isolates, it doesn't allow carriers to flow. That's why its isolation is acting. So the wafer is first oxidized and the windows are etched there, and finally using photolithography technique, and then isolation is developed. This is isolation required. This is how we can form, we see, N. Between N and N we have this. This is called isolation. Between N and N we have this. That is called isolation. So therefore, isolation is possible using a junction. Question number 9. Explain bipolar NPN transistor fabrication. How actually NPN transistor is fabricated? See, any bipolar transistor can be fabricated in this way. First you take a substrate. Upon the substrate, using epitaxial, you put the N layer, and then it becomes PN. And then you put another layer from outside using diffusion. Therefore, NPN becomes, that's how the total NPN is developed. That's the process. You can see here, you have NP, and then you see N here, and then N, P, is it? NPN. So, of course, all this is developed upon substrate. Every device is developed upon substrate. Question number 10. In integrated circuit, the design of electronic circuits is based on the approach of use of maximum number of resistors in the circuit, large sized capacitor, minimum chip area irrespective of the type of components in the design, use of only bipolar transistors. Why? What is the main thing? An integrated circuit is the design of electronics based on which approach? In integrated circuits, the design of electronics components based on the approach used. Minimum feature size, number of gates, power dissipation, gate delay, die size, testing, reliability and production cost. So these are the different reasons why we go for what you call manufacturing of ICs. That's how we finish illustrative problems. So therefore the option is C. What is option C there? Minimum chip size area irrespective of the type of component. So minimum chip size area has become, this question is asked in IES 2006 and that is option is C. Question number 1. The primary reason for widespread of use of silicon in semiconductor device technology. The option everybody knows. The abundance of silicon on the surface of earth. If you see ABC here, abundance of silicon on the face of earth, this is asked in GATE EC 2005, 1 mark. The more interesting point is abundance. Option is A. Question number 2. In integrated circuit, the silicon dioxide layer is providing what? Electrical connection, physical strength, isolation, conducting. IES 99. Very simple, as I told you, isolation. Option is C. Isolation. Option is C. Question number 3. In the fabrication process, buried layer, NPN transistor, the process involved are diffusion, oxidation, epitaxial, lithography. What is the correct sequence in which the steps are taken? That is asked in IES. Options. The first step is lithography. That means we cut. Then we do oxidation. Then we do epitaxial. And then finally we do diffusion process. So therefore, if you see the numbers that are the sequence, the option is D. So arrange the numbers according to this sequence. The sequence they gave was diffusion first, but the sequence is 4, 2, 3, 1. That is it. 4 means lithography, then oxidation, then epitaxial, lastly diffusion. That's the process we normally take for IC fabrication. Question number 4. In the fabrication of NPN transistor in an IC, the buried layer on P-type substrate, is it P plus doping, N plus doping, used to reduce the parasitic capacitor, located in the emitter region? IES, question 2003. Which one is actually used for buried P substrate? If you see the option there, it is B. In the fabrication NPN transistor in IC, the buried layer on P-type substrate is N, because you see this is substrate. What is that actually? We use N. If the substrate is P, we have to use N. That is why option is B. B means N plus doped. Question number 5. Which one of the following statement is correct? In the context of IC fabrication, metallization process, connecting mechanical wires, formation of interconnecting conduction pattern on bonding pads, doping silicon dioxide layer, covering with metallic cap. It's also asked in IES, what is the correct thing we are doing in metallization? Solution. In IC fabrication, metallization means formation of interconnecting conducting pattern and bonding pads. That means option is B. So what exactly we do in the metallization, we have explained here. That's a process. Question number 6. Consider the following. First, cheaper method. Lower residual oxygen content in grown crystal is possible. Uniform doping is possible. larger diameter crystal can be grown. Which of the following above are advantages of float zone FZ method over CZ method in a single crystal growth of silicon? Which one is more advantageous? The options are 1 and 2, 2 and 3, 3 and 4, 1 and 4. The option is B. Compared to CZ method, FZ method has low residual oxygen content. That's why that is preferred. So option is B. B means, look at here, 2 and 3. Low residual oxygen content, uniform dope. That is the answer. Seventh question. Consider their following statements. X-rays are used for lithography technology because high resolution is achieved, scattering effects are small, they can be focused easily, they can be deflected easily. Which of the following statements given above are correct? There are so many statements given. Which are the statements are correct? There can be more than one. So look at here. X-rays are used for lithography, that already I made it clear, because high resolution is achieved. So the option is A. What is A? Look at here. 1 and 2. High resolution is achieved, scattering effects are small. Because of the first and 2, X-rays are used. So nowadays X-rays are preferred even compared to other technology of lithography there. Question number 8. The base function buried n plus layer in NPN transistor in IC is 2. What is the base function? What is the main function? Is to reduce the magnitude of base spreading resistor? Or is it to reduce the collector series resistor? Is it to reduce the base width of transistor? Or to increase the gain of the transistor? What for is the main purpose it is used? This you asked in IES 2005. The base function buried n plus layer in a NPN transistor is used to reduce the collector series resistor. Collector series resistor means option is B. So that is why it is used. We can reduce collector series resistance. Problem 9. Which one of the following statement concerning IC fabrication is not correct? A typical wafer of silicon, 400 micrometer, thickness, diameter 5 to 15. The purity of the wafer does not matter and can be even polycrystalline in nature. Second one, resistors are obtained by utilizing the bulk resistance of one of the reasons. Third one, semiconductor lacks magnetic material. Fourth one, in reverse biased PN junction, positive and negative ions exist. So which one is correct concerning IC fabrication? Solution. In IC fabrication, the semiconductor material is used to fabricate devices in a single silicon crystal with a very high purity and in the form of flat circle slices. Therefore, our option is A. Option is A. This is the reason why and how, what is connected concerning ICs. 10th one. The process of extension of single crystal surface by growing a film in such a way that the SS atoms from a continuation of a single crystal is called the process of extension of a single crystal surface. What is it? Is it ion implantation, chemical wafer, electroplating, epitaxy? This is asked in IES. The answer is epitaxy. Epi means upon. It is a process used to grow a thin crystalline layer on a crystalline substrate. Any small thin layer, if you want it to go for epitaxy, and that's called epitaxial layer, as I already told you. So therefore, option is D. So this is all about what you call different ideas related to IC fabrication. This is what I mean device technology.